our ARCS Foundation Honolulu chapter Hana program. ARCS Foundation is a national organization that supports science in America through unrestricted grants to outstanding college students in STEM fields and health sciences and mathematics. Our Honolulu chapter was founded in 1974, and we've provided about $3 million in support for graduate students here at the University of Hawaii at Manoa. So along with the work that we do to raise funds to provide these grants, we also like to learn about the sciences. We're a group of women who are interested in, believe in science, but not necessarily a heavy science background ourselves. So with that, I'll introduce our speaker who just sat down, Dr. Stephen, I forgot to ask, Businger?
Very good.
Okay, not a soft G. Businger is a certified consulting meteorologist, hence our little weather report, if you caught that before we got started. He's professor and chair of the Atmospheric Sciences Department, which is in the School of Ocean and Earth Science and Technology here at UH Manoa. And he leads the Storm Evolution and Energetics Research, or SEER group. He's been principal investigator who's brought in more than $7 million to the university since 1996. And he's received the Chancellor Citation for Meritorious Teaching. So full package, both teaching and research. He's co-creator of the Rainbow Chase phone app, which is available free. And I hope he's going to tell us a little bit about that so that you can chase rainbows if you'd like to. And important to us, he's advisor to one of our 2022 ARC scholars, TJ Corrigan, who's on the mainland chasing storms this summer for his research. And you may have seen the two of them quoted in the paper within the last month about the superstorm over Hawai and research about what produced that and what might help understanding the dynamics so that those kind of events can be better predicted in the future. So with that, I'm going to turn it over to Steve.
Thank you very much for that intro. So I will, thank you. I will do a combination of two things. One, I can use a laser pointer, but only you can see it. So I'm going to also do this and kind of go around. Turn this. Okay, so I'm going to talk today about the secrets of the best rainbows on Earth. Take the cat's out of the bag. We all know that we have the best rainbows in the world. This is a shot on Kauai, Halalau Valley. Most of the photographs in this presentation are my own, but not all of them. There are a few exceptions. So there are four parts to my talk: the cultural and historical significance of rainbows in Hawaii, the science behind the rainbow phenomena, why is Hawaii the rainbow capital of the world, and lastly, chasing rainbows, which has a little bit to do with the phone app, but it also has to do with something a little different, which I'll explain in a minute. A nui nui is the Hawaiian word for rainbow. And it turns out the Hawaiians really revered rainbows, as I think we all do. They're kind of an amazingly captivating atmospheric optic. And the Hawaiians have many, many names for rainbows. And that's, I think, a reflection of how common and how beautiful the rainbows are in Hawaii. So they have names for things like a rainbow fragment, a barely visible rainbow, or in the case of this rainbow here, a lunar rainbow, on the Nui Nui Kapau. So that's a lunar rainbow. If you look close, you can see stars in the background here. And we do see lunar rainbows in Hawaii. Very difficult to photograph. You have to have a tripod and open the lens for a bit. But what about, the way that Hawaiians historically thought about rainbows? And it turns out that they viewed the rainbow as a symbol of transformation. So in Hawaiian mythology, they considered the rainbow a pathway between dimensions, between the earthly and the heavenly realms. And I think that's a beautiful concept. Often when I'm looking at a rainbow, I feel transformed. I feel like it speaks to the spiritual side that I have. By the way, this little piece of a rainbow here is called a kahili. Kahili is the Hawaiian word for a standard that the ancient Hawaiian chiefs would have that had a big plume of feathers at the top. You may have seen those. And so when you get a small vertical piece of a rainbow, they refer to it as a kahili. So we are in Manoa Valley, and it turns out that there are a lot of rainbows in Manoa Valley. That has to do with things that I'll talk about a little later. But it turns out that there's a Hawaiian legend that goes along with the rainbows in Manoa Valley, and that is that it is the presence, that the rainbow signifies the presence of Kahala Opuna, who was the daughter of a chief and chiefess who lost that daughter to a jealous suitor. And so the chief and the chiefess transformed themselves into the rain and the wind of Manoa Valley. And then when the misty rains catch the rays of the sun, then Kahalapuna appears in the form of a rainbow. I like this. This is in near Wailua on Oahu, and they have a beautiful sunflower agricultural zone there where they grow sunflowers. And the Hawaiians had a saying, "Mohala ike anue nue kamaka o kapua," which translates as "unfolded by rainbows are the faces of the flowers." And I think that that's just so appropriate, right? So next, I mean, obviously I could speak for a whole hour on the cultural aspects of rainbows, but I want to talk a little bit about the science, because the science feeds back into why it is that Hawaii is the best place for rainbows. So going back to the earliest writings on rainbows, we have Aristotle in 350 BC, noted that rainbows have a specific shape, and he postulated that the appearance of a rainbow was a reflection of sunlight on a distant cloud. We know today that it's a reflection of sunlight by raindrops. So and I expect that he knew that too, but he didn't write that. So you kind of wonder. The Arab scientist Avicenna, around 1000 AD, was aware of the necessity for sunlit raindrops. And Iris is the Greek goddess of the rainbow. So the Greeks had a god for the rainbow. There is a darker band between the primary rainbow and the secondary rainbow, and with more light being dispersed on the inside and on the outside of the bow, but a darker area between the two bows. And that was first described by Alexander of Aphrodisia around 200 AD.
Look at that.
Yeah, so that's quite a long time ago. And Roger Bacon in around 1200, I think, get rid of these controls again, they keep coming back. Around 1266, he described the rainbow in terms of the angular extent, and he was the first to do that. He said the primary bow is 42 degrees above the shadow of your head, and the secondary rainbow is about 8 degrees above that. Now, René Descartes was really the first scientist to fully explain the geometry of the rainbow. And the way he did that was through ray tracing. He created a water-filled glass sphere, and then he allowed light to hit the sphere, and he followed the rays, and he created the law of refraction from this. He derived the law of refraction. Turns out he wasn't the first, but he didn't know that Snell had done that, a decade or so earlier. But he carefully did ray tracing, and what he discovered was that if you go above the rays that form the rainbow, that those rays come out on the inside of the drop, and they don't contribute to the rainbow. They contribute more to the light that's on the inside of the bow. But there's a certain angle at which there is a concentration of sunlight coming out of the drop. And also that's an area where you have dispersion because of the refraction. Although interestingly, he never looked at white light as being divisible into colors. So he didn't actually describe that. That came later. Sir Isaac Newton was the one. So the primary bow, the light comes in, it reflects once at the back, and then it comes out, and it refracts on the way in, and it refracts on the way out. So there's two refractions, and there's one reflection at the back. And that results in an angle of 42 degrees. Now the secondary bow, the light comes in lower on the droplet, and it has two reflections, 1, 2, and then it refracts on the way out. And it comes in 8 degrees higher than the primary bow. So it's higher in the sky. So this is the primary bow, this one here, and the secondary bow is up here. And I thought this was a pretty clever diagram that he put together and published in 1637 that described all this detail about the optics. But as I mentioned before, Descartes did derive the law of refraction, but it was Wilbrord Snell back in 1621, a Dutchman, who first derived it. And he showed it in water that you have this refraction, and that it has to do with the change in the speed of light. As it goes from air into water, the speed of light changes. We've all heard that the speed of light is constant, but it's only constant in a vacuum. And then if you have various media that it's passing through, the speed of light slows down. Diamonds slow the speed of light the most and have the highest refractive index. That's why people like to wear diamonds. So the Snell's law is simply that the sine of the angle 1 here divided by the sine of angle 2 is equal to the ratio of the velocities, and that's equal also to the ratio inverted of the refractive indices of the two media. So water has a refractive index here, which would be N2. So Alexander's dark band here can be explained by the fact that there is so much light that is coming out of the drop. This is the incoming rays. Maybe I should do it here too. The incoming rays are over here, and the outgoing rays are these ones here. So there's a lot of light pollution coming out of the drop, and that's what you see above on the rainbow. Yet there's a very sharp cutoff, and that cutoff is indicated by this area here. And that cutoff for a double reflection, there's the secondary bow, two reflections. There's a lot of potential for light to escape the drop on the back side, which is out here. And so in between those two, you have this area of darkness called Alexander's dark band. So that explains why you have that dark band. Now, interestingly, if you take a raindrop, and in this case, I've got a quartz crystal sphere, and illuminate it with flashlight, that sphere will cast a circular pattern of light on the wall. So in essence, what's happening is that the raindrop produces a cone of light. We call those rainbow cones. So each raindrop doesn't just produce one ray going in one direction, it produces a whole cone of light. And there is more light that escapes on the inside, and there's a sharp cutoff on the outside with darkness beyond. That sharp cutoff area is where the rainbow forms, right on that edge. And we call that the Descartes ray. It's this area right here. And if you take a photograph of a droplet and have it out of focus, you'll see that an entire rainbow comes out of each individual dew droplet. But if you focus on the drop, it'll only give you one color. And so a rainbow is made up of light from many, many droplets, where each droplet is just providing one color to your eye. So here's the rainbow cone from each droplet. The rainbow cones are shown here on the left. And each rainbow cone is casting into the atmosphere a colored bow. But you as an observer are seeing bits of color from many different droplets, millions of droplets, to produce the rainbow. You're taking individual rays out of each of the rainbow cones that are cast by the individual rain droplets. So what that means, essentially, is that if your friend is standing right next to you, looking at the sky, the rainbow that he sees is constructed from individual rays of light coming from different raindrops than the raindrops that you're seeing in your drop, in your bow. And so each person sees their own unique rainbow. Now, one of the things that make chasing rainbows a little tricky is that if the sun is too high in the sky, the rainbow ends up being below the horizon. So if it's too high, it ends up being below the horizon. So you need to go early in the summertime, early in the morning, to find your rainbows, to chase the rainbows. You need to be when the sun is relatively low. Now you can also do rainbow chasing in the afternoon, but there are more showers in the morning. So morning is a good time. And I have a little animation here. It's not animated. Let's try it again. Okay, here goes. So it starts off with the rainbow being tallest when the sun first rises. And then the rainbow shrinks in size as the sun rises. So you want to get out there early while it's still above the horizon, because otherwise it won't be a bow. So early in the morning or late in the afternoon, this is an afternoon photograph, you have a tall rainbow. And of course, if you're standing high on a ridge, you get to see more of the rainbow. If the sun is higher in the sky, but not too high, the rainbow will just lie flat on the horizon, and you'll have a series of colored bands. This is taken with a telephoto lens in over Lake Washington, Kirkland over here. That's close to Microsoft. And yeah, you can see these different colors, really low because the sun is relatively high in the sky. Now, I mentioned before that Sir Isaac Newton was the fellow who actually said, hey, light is composed of all these different colors. And if you mix those colors together, you get white light. But actually, the light has all these colors implicit in it. And you can look at that and you can see different shades of color and you can give them names. Well, he called this a spectrum, and he said, well, you know, there's 7 days in the week. There are 7 planets in the solar system. There are 7 musical notes in a scale. So, of course, the rainbow has 7 colors. And the Hawaiians said, nah, you're wrong, Sir Isaac Newton. You don't know what you're talking about. I see 1, 2, 3, 4, 5 colors. So the Hawaiians typically thought that the rainbow had 5 colors. But, you know, we can see hundreds of thousands of different shades and we can give them all names. So it's completely arbitrary how many you want to give a name to. But Sir Isaac Newton has given us the colors of the rainbow. They are red, orange, yellow, green, blue, indigo, and violet. Those are the official colors of the rainbow. Now, here's an interesting photo taken out surfing in the North Shore. The wave, when it is moving across the ocean, it actually moves pretty fast. The bigger the wave length, the faster the wave moves. And as the wave is breaking, it's throwing a lot of spray into the atmosphere, and it's casting this spray thing here. And that's salt water. Salt water has a different refractive index from fresh water. And therefore, you have a rainbow that is inside a rainbow behind, which is in natural fresh water. So the refractive index is a little bit bigger for the salt water, and therefore the angular distance is a bit smaller. So kind of an unusual thing. Here's a rainbow taken by Honolulu Harbor. And it turns out that if you really look closely at this, you think to yourself, okay, well, it's pretty obvious that it's just a simple reflection, right? It's just a simple reflection, but it's not. And I'll tell you why it's not a simple reflection. This rainbow is created by a cone of droplets. This rainbow here, reflected in the water, is a screen. It's a 2-dimensional thing. So you have a 3-dimensional object here, and you have a 2-dimensional object here. And if you do the ray tracing, it turns out that this reflection does not map to this exact same set of droplets as the rainbow above. It's a little hard to wrap your head around that, but if you do the ray tracing, it turns out that you're looking at two sort of, the reflected bow is not simply a reflection. So around the turn of the last century, there was a fellow named Gustav Mie, and he came up with a theory, and it took into account that light is a wave and not just a particle, like Newton thought. Newton thought that light was just particles, photons. But what this diagram shows is radius of a raindrop on the left-hand side, and then it shows the scattering angle. And so this is the primary bow, and this is the secondary bow. And what it's showing is that for a large droplet, you get a brighter bow. And for very small droplets, you start losing the rainbow altogether. And that has to do with that the colors, because the wavelength of light is getting closer and closer to the size of the drop, the colors get smeared. But look at all these other things in here and over there. Those are supernumerary bows, and I'll talk about those in a minute. They're because of the wave nature of light, those can exist. Something keeps popping up here. The previous diagram had one at the top. So this was the top of the previous diagram, but these are all much bigger droplets. So this is what happens when you get really big raindrops. They get flattened at the bottom. And what happens is that the spherical shape of the drop is maintained in this direction, but it's not maintained in this direction. And so the rainbow on the sides stays put, but the rainbow at the top moves, shifts. And that creates some really strange things like this, where you have a twinned rainbow. This is due to a combination of smaller droplets and bigger droplets. So you have two distinct populations. One population is creating this bow, and the other population is creating that bow. So it's one of those things that you can rarely see in Manoa Valley when you have the fine mist creating one bow and there's a shower that's coming through that's raining all of a sudden hard, and it creates this bizarre thing.
What about the other one on the top?
That's the secondary bow, and that's due to two reflections at the back of the drop. And I mentioned diffraction causing supernumerary bows. This is an example of that. So inside the primary bow, you have this possibility of interference. It's an interference pattern, which is indicated here. Kind of a moire pattern that is created here. And you have positive and negative interference. So you have constructive interference in some places, giving a bright spot here for red light, and there's a bright spot here for green light, and here, and this is for purple light, because they have different wavelengths. So when you put this all together, you end up with a rainbow pattern. That rainbow pattern is what you see on a compact disc, a CD, with music, because the grooves are just the same size as the wavelength of light, so it creates a rainbow. Same thing with droplets, if they are small enough. This is a little difficult to understand, but I'll just tell you what the bottom line is. It's that rainbows are polarized. So if you look at a rainbow without sunglasses or with non-polarized sunglasses, you'll see this. And if you put on your polarized sunglasses, you'll see that. And that's one of the reasons that I don't wear polarized sunglasses in Hawaii or anywhere for that matter. And it's kind of hard to find sunglasses that are not polarized because it's so much what people look for. They want polarized sunglasses. But it turns out that you're going to miss this rainbow by wearing polarized sunglasses. Don't do it. Now, here's another strange one. This happens when you have water that's relatively calm, reflecting the sun and producing a rainbow here. This is a secondary bow and a primary bow from the reflected sun. And these are from the sun itself. And to understand this a bit better, you can see here's the reflected sun comes up, has a different angle, it's higher, and so the primary bow sits higher than the normal primary bow from the direct sunlight. And you have this, you end up with this pattern. This is the primary and the secondary bow for the direct sun, and then this is for the reflected bow. They're sitting up above. As the sun sets, it gets kind of red sometimes, especially if there's a lot of fog in the air. The sun becomes very red. Well, then you get these red rainbows. And that has to do with the atmosphere and pollution in the atmosphere scattering the red and green light out and leaving you only with the red light. So why is Hawaii the rainbow capital of the world? Let's look at that. Well, if you Google rainbow and Hawaii, you end up with a tremendous number of photographs. If you hit images, just millions of photographs. And in fact, you can study these in order to figure out more information about rainbows if you do it globally. And we've done that to see how climate change is impacting the distribution of rainbows. And I'll come back, maybe comment on that at the end. But look at how many of our commercial operations and the Rainbow Warriors for the University of Hawaii teams and the rainbow on our license plates. Even the stamp for Hawaii has a US Postal Service stamp has a rainbow on it. So lots and lots of, let me admit, lots and lots of possibilities there. Rainbow Warriors. This is a friend of mine who helped produce the Rainbow Chase app for the phone. His name is Paul Sin, and he drives a rainbow car.
Wow.
So why is it that Hawaii has great rainbows? And the answer, I will explain, basically has to do with these three aspects: the bright sunshine, the fact that we get a lot of rain showers, and then also geometry plays a role. But let's see. So I mentioned earlier that we live in the trade wind belt before the talk started, I guess. And the Hawaiian Islands are here. You have strong convection taking place along or near the equator. The doldrums, they're called, or the intertropical convergence zone. And then that leads to rising motion here and southwesterly winds aloft, and then sinking motion. And the sinking motion comes right along about 30 degrees north and south of the equator. That's why those are the desert zones of the planet. The Great Australian Desert, the Sahara Desert, the Desert Southwest, all are related to this global circulation with rising motion at the equator, sinking motion at 30 degrees north, and northeast trade winds. Now, we are in the northeast trade winds. Here are the northeast trades blowing toward the southwest, and here are the upper level winds coming from the southwest, and that is the Hadley circulation. It looks like it's really deep if you look at it in a schematic. But it turns out that the atmosphere is really shallow. And so we're only talking, a few miles between those two. So why is that important? It turns out that if you look at satellite photographs, we all know that if you fly from the west coast, you tend to first see a lot of stratus, marine stratus over here. And then gradually you start seeing pancake clouds. You see these pancake clouds that have a certain shape to them. Eventually, though, when you get closer to Hawaii, all of a sudden you see mostly ocean and sunshine with cumulus clouds. And we call this open cell convection. This kind of a pattern here has good updrafts in the places where there are clouds, which results in showers. This is a little complicated, so I think I'm going to skip it because I'll talk about all these things as I go along anyway. We know that if the wind is kind of less and there is heating of the island, you get a circulation called a sea breeze circulation. And the sea breeze tends to create deeper clouds over the islands. On the other hand, if the flow is stronger and stable, then you get these flat clouds on the islands. But in both cases, you can get precipitation over the mountains, and that results in oh, let me try to kill this thing once more.
And he said if you drag it out of the way.
Oh, yeah, maybe. I'll try that next time.
Okay.
So this loops, basically what it's showing is the trade wind circulation and the island impacts. So the big island casts a great big wake, sort of a bow shape here, and that takes precipitation all the way over to Hawaii, Oahu, from Hawaii to Oahu. And in fact, you know, this corner of Maui gets an awful lot of stuff coming off of the Big Island, right like that. And it turns out upslope from Maui is one of the wettest places on Earth. It rivals Waialeale on Hawaii as the wettest place on the planet. But here you can see that the koalas are perfectly oriented to capture and generate precipitation. And to the lee, there's an awful lot of sunshine. Perfect conditions for rainbows. And here is just a map that shows the koalas, and it actually doesn't show any terrain. What it's showing is red is upward motion and blue is downward motion. So basically what goes up on one side of the mountains comes down on the other. And that's why it is that you tend to have sunshine in Waikiki, and at the back of Manoa Valley, you tend to have rain. And that is illustrated here too with the annual precipitation. Very strong gradient from 160 inches of rain at upper Manoa Valley to 20 inches in Waikiki. Very strong gradient in the rainfall. And as a result, you see wonderful rainbows in the lee. And this is Hawaii Kai. This is a photo taken from a former house of mine. This is called a punakea, this little rainbow here, because it's not very distinct. It's not a real strong rainbow. So we call that a punakea. Daily heating is that let's see if I can drag this off. Maybe I can. Looks like everything close to it. Yeah, doesn't want to drag. Oh, well, doesn't matter. So the islands heat up and it causes there to be a sea breeze. Daytime heating causes upslope winds. And let's see, this is a nice animation. Watch the Big Island for a minute. Because during the day it heats up, sea breezes. Now this is under light wind conditions, right? Also Haleakala, both Kauai and Oahu have sea breezes under light wind conditions. Perfect conditions for rainbows. You have sunshine coming in the morning and the afternoon, and you have, especially in the afternoon, under these conditions, you have showers. So this is the amount of cloudiness that you have over Oahu. Look at the gradient. A lot of cloudiness over the Ko'olaus, and even on the windward side and the North Shore, you get these areas of sunshine, lots of open sky for the sun to get in to give lots of rainbows. On the Big Island, you have the sea breeze circulation across Kona in the afternoon. This is 2 p.m. in the afternoon. It's kind of a composite of a month's worth of data. And here's taken from Mauna Kea looking down towards Kona. And you can see the air wants to come up, but it gets a limit because it only has so much kinetic energy, and the mountain is so huge that it has insufficient kinetic energy to make it beyond this point here. Now, what's the significance of that? Well, it means that you've got an area of upward motion and shower generation in a line that allows you to see rainbows. On both sides of that line, you can see rainbows. And here again, here's the precipitation from that area. So if you're down in Kona, you can look up mountain and see rainbows. Or if you're a little bit more upland, you can look down and see rainbows. And similarly, the Hamakua coast is, of course, gets a lot of precipitation. So clean air means bright sunshine. That's one of the key ingredients for having good rainbows is you need to have bright sunshine. And we have very clean air in Hawaii because we're so far from pollution sources. We don't have a lot of forests for pollen to be generated. We don't have continental dust or pollution. And as a result, we have very clean air. From satellite, you can see, you know, the green on one area and the drier conditions in another part of the islands. And that gradient is perfect for seeing rainbows. But now this clean air, it means that there are fewer particles for clouds to condense on and form rain droplets or cloud droplets, right? Cloud droplets need to have condensation. And there are very few here, mostly from salt. And that makes the cloud droplets larger and more able to coalesce, which is shown here. This is in the lab. You have a blue droplet and it's coalescing with a clear droplet. So that is what is generating the rainfall in these very small clouds over Hawaii. If you go to the mainland, the clouds this small will not rain unless you're right on the west coast and the air is coming in from the Pacific. Then you could have this. But if you're in Arizona or Colorado, forget it. It will not rain out of a cloud this size because you have too many condensation nuclei. The droplets are too small, they won't coalesce. So you need something else. But that's a different lecture. Hawaii, we have warm rain out of very, very small clouds and they produce rainbows. Diamond Head is one of the best places in the city to see rainbows. Really good place. This is a coronal low, and what I want to show with this is in the wintertime when we have coronal lows, look how showery this pattern is. And those little bright spots there, that's lightning. So lots and lots of opportunity for rainbows in coronal lows. Here's a cold front. We get cold fronts in the winter, and look at how thin this line is. This is a relatively weak cold front because it has passed over a lot of tropical ocean and basically is dissipating. But when it comes through, the air behind it is moist and very stable, and it creates this wall of cloud over the mountains and a rainbow in the lee, and that rainbow can last all day. Maybe some of you have experienced that in Manoa Valley. You look up the valley in the morning, the rainbow is in the west. In the afternoon, the rainbow is in the east, right? It's just moving from one side of the valley to the other over the course of the day. You can have rainbows that last for hours. So here's my last little bit talking about finding rainbows. And what I'm looking for is a circle rainbow. And to photograph a circle rainbow, you have to have a very wide angle lens. And this is a photograph taken from my dining room into my living room, just kind of indicating how wide an angle you need. And first you look at the weather map. I mentioned that there's a lot of moisture in here, so it's a good day to fly. There's the radar is showing some precipitation and a lot of sunshine, so let's go. And we take a helicopter from Honolulu Airport, and we head towards Kauai. And there's nothing on the way, but as we get close to Kauai, we see this shower just in the lee of Molokai. Did I say Kauai? I meant Molokai. So I'm approaching Molokai in a helicopter, and then the pilot stops and he turns the helicopter and I hang my camera out and I take this picture. This is almost straight down, and this is, you know, a full circle rainbow. I will try one more time. Get rid of those meeting controls. I don't like them. So here we have 360-degree rainbow. Now, Molokai, as you know, has big, tall sea cliffs, so there ought to be a good place to generate some rainbows there. But it turns out that there was too much cloudiness on this particular day, so we didn't see much there. And by the way, this is Kalaupapa. We parked there for a minute to catch our breath. Heading back, I see this interesting cloud here. This funny shaped cloud is a lenticular cloud, or a mountain wave cloud that's generated by this area of Molokai. And what's special about that cloud is that the air passes through it very quickly, and then it disappears. And so the droplets are all uniform and small, and it allows this little rainbow to form. This is called a glory around the shadow of the helicopter. So right there, that's a glory. And then you have in this part over here, that's a supernumerary bow. And this over here is called a fog bow or a cloud bow. The droplets are too small to generate a rainbow. So this would be a rainbow if the droplets were larger, but it's too small. And here is another day. This was last November, just before Christmas. We went out again and we were photographing the circle rainbow just off of Police Beach, I guess it's called, near Haleiwa. And then the other one, just to give you motion sickness, this is the other rainbow that we caught just a little bit closer to the Dole plantation. You can see all the pineapples down below there. So yeah, that's enough to make you seasick. So we fly with no doors on the helicopter. And one of the things that you have to worry about is that as you're translating from point A to point B, the wind can be 150 miles an hour outside this door. And if you get excited about something and you go like this with your camera, all of a sudden, there goes your $5,000 camera. So luckily, that hasn't happened to me because I was forewarned. But isn't that a great Christmas card?
Oh.
That is the beach just north of Haleiwa. Here you can see the windmills. There's another one. And lastly, my Rainbow Chase app, what it does is this is showing Washington here because it's going national, but essentially it started in Hawaii. And this arrow here is the direction of the sunlight. And this is the 42-degree angle that allows you to see rainbows. So you just face yourself in the direction of that arrow and you look for these little guys. Those are the rainbow potential. And so, and you can go to rainbowchase.com, and you can download the app, or you can go to your app store, whatever one you use. And it gives, the current weather, it gives radar and satellite views, and it gives you that special ability to know where it is the rainbows will be. You can see whether there's a rainbow in your area. And I'm hoping to eventually have some contest where people can take photos of the rainbows they see and send them in and have the photo of the week, that kind of thing. And the whole idea is to just have people become more aware of the atmosphere, start looking. Well, and if you do look, rainbows are amazing. I mentioned that climate change is going to change the distribution of rainbows. Well, you can imagine that Iceland in the wintertime doesn't have rainbows. It's too cold. But what about if you have some global warming? It's going to bring more rain to Iceland and you're going to have more rainbows, more potential for rainbows. So generally speaking, there will be more rainbows at higher latitude, more thunderstorms in places like Alaska where they don't normally have them. And there will be less rainbows in that sort of belt where we see a lot of drying and drought, like the Southwest United States, California, and maybe Oregon and Washington will see less rainbows. Hawaii, we have a lot going for us, so we'll probably see a lot of rainbows anyway. But yeah, global warming is not necessarily good news for Hawaii either for rainbows. Now, it turns out that there are also other kinds of things that produce colors in the sky. And I just wanted to point that out. This was taken in Sweden, and it's 22 and a 46-degree halo with a circumzental arc here, upper and lower tangents, sundogs. I mean, there's a whole litany of stuff there. It drives my one-on-one students nuts when I ask them to tell me what's there. That's my last slide, this one here. And I have a question for you. What's wrong with this picture? Yeah, there's not, that's wrong. Turns out there's 5 things wrong with this. So there shouldn't be a rainbow there. Can anybody see anything else that's wrong? Yeah.
The outer rainbow is in the same configuration as the inner one. It's not opposite, like you said.
Yeah, that's right. The color should be reversed here. So that's number 2. What else is wrong with this picture?
Doesn't look like it's raining.
Yeah, that's true. I can give you a 3 for that one. You know, you don't have a dark band, right? Alexander's dark band is missing. There's no, you know, like mist in here. Normally you would see some evidence of rain in here from all the scattering from inside the droplets. So Alexander's dark band. Anything else?
Isn't it supposed to be lighter, more brighter in the inner?
Yeah, it's supposed to be brighter in here, but yeah, you're hinting at another thing, which is,
Direction of the sun.
yeah, the direction of the sun is totally wrong. The sun has to be behind you. You're looking away from the sun, directly away from the sun. So this should be lit up, shouldn't be in the shade. Yeah, very good.
There's no green in it, is there?
There is.
Oh, okay.
Not much.
Yeah, no, I mean, this is a Hawaiian rainbow. They only had 5 colors. Yeah. So, well, thank you very much. And thank you to the and thanks to the Zoom audience too. I'm happy to take questions. If anybody out there in Zoom land has a question they want to type in, they can do so.
Go ahead. We have a question in the back.
Yes, you had a slide that had all the different Hawaiian names for their different rainbows, but I didn't see if there was a particular name for the double rainbow.
Oh, you know, that's a great question. I'm sure there is, and I don't know what it is. But yeah, I'm sure that it has a separate name. Go ahead.
I swim in the ocean in the morning,
Yeah,
and if we're swimming Eva, going toward Eva, we often see double rainbows, like almost every morning.
yeah.
But I have occasionally turned back toward the, well, looking out.
Yeah.
And I'll see one to my left, which doesn't sound right. Now that I listen to it.
Okay, so there's a couple things that could be happening. You know, a rainbow is big in the sky.
Right.
And sometimes you'll have a shower over here that'll give you a really nice rainbow, but it stops with the shower. And then there's a shower way over there that is giving you the other part of the rainbow. That could be an explanation. There is such a thing as a third rainbow or the third reflection that is towards the sun. But no one has ever, to my knowledge, photographed it. So I think that the solar radiation kind of wipes it out. I have seen photos of the fourth reflection, which is between the primary and the secondary bowl. So it would be like right in here. And I have seen a photo of that. But there are fifth, sixth, seventh, eighth, ninth reflections. There's all these reflections. But every time you're losing light out the back of the drop. So these further rainbow possibilities are not seen in nature.
I'm curious if this is a hobby or if you're trying to add to the scientific theories and rules governing rainbows.
I'm trying to get more students to come to Hawaii. Photography is a hobby of mine. I really love to do photography. And I love to take photographs of beautiful things. And I am driven by this spiritual feeling that I get from my photography and from seeing things in the air. And I want to convey that to my students. So I'm very active in incorporating things that I photograph into my lectures to explain what it is that's going on in the world around us. And I would say that's a lot of what drives me to study rainbows. And I had a sabbatical when I wrote the rainbow paper, The Secret of the Best Rainbows on Earth. And it was during COVID. And I thought, well, what a good way to maybe lift some spirits. But as far as getting funding from the National Science Foundation to further the science of rainbows, it's not very easy. They're not too receptive.
I have a question. What would happen if you had some tremendously strong instrument? You could see the light from a single raindrop as it's coming down. What would that look like?
Oh, well, it would go from red at the top, it would gradually go through the whole spectrum of colors.
Would it change immediately as it goes from red to orange? Or would it?
No, it would be super, super subtle, you know, and especially if you did it in slow motion with high resolution video camera, high time resolution, so you caught the dropping. It would go through these changes in color very gradually.
I see.
Yeah, that's a great question. I think that's a fun one.
So when you say you're looking at a rain, I mean, those are raindrops, but you're looking at a raindrop, and each raindrop is just showing you one color, even though it's emitting all the other different colors to someone else who could see it.
Yeah. But you bring up a good point. You know, when you're looking at a rainbow, it's like looking at a waterfall, right? The water is continually going down the waterfall. Similarly, the rain in the rainbow is continually going down through. And each time there are new drops at the top giving you the red. And as they fall, they go through all the different colors as they come through. And so it's a very interesting thought. Yeah.
That's why there's a fallacy about the pot of gold, because the rainbow is moving all the time.
Well, I actually saw a picture of an outhouse with the rainbow falling right on top of the roof of the outhouse. So I don't know, there may be some special cases. But yeah, you know, the other question is, I think I even have that on a slide here. Since the rainbow is in reality a full circle with no end, does the end of the rainbow exist? And now we do have some questions here that maybe have come in, so let's see. If I can.
We did have a question about recording, so we will be posting this video. It takes a little time to edit it. And if you signed up, anyone on the Zoom call will send you the link, and I'll also send you the link to the paper that Dr. Businger mentioned on Hawaii being a special place for rainbows. If you are attending in person, I put a sheet of paper there. You can leave your name and email, so I'll send the link to you as well.
So I will make available to anybody, including you, of course, Cheryl, to the slides from my slideshows and as a PDF so that you can share that too. But somebody asked, will this be archived? I guess you just answered that. Look forward to watching this again. This is terrific. Can't wait to share this presentation. Okay, don't see any other questions at the moment.
Any other questions from the group here?
Well, thank you very much. It was fun to come and talk about rainbows, my favorite topic.
Thank you so much.